Hello, and welcome to the Load-Modulated Balanced Amplifier with Dr. Steve Cripps. I'm Mike Hamilton, your host for this IEEE Microwave Theory and Technique Society webcast, which is sponsored by National Instruments. Before we start, I'll mention a few housekeeping items. First, this presentation will be archived. A recording should be posted approximately 24 hours after we finish the presentation. We'll send all registrants an email when the archived webinar goes up so you can revisit it or share it with your colleagues. Second, we encourage questions. We'll answer them after the presentation, but you can submit them at any time during the presentation. Enter your question in the Q&A box in the webcast window and don't forget to click Submit. Third, some words about the interface. You can enlarge slides by clicking on the rectangle at the top right of the live slide window. You can also enter full screen mode if you desire. Refresh or reload the current web page if you encounter any problems. With regards to audio, if you're listening over your computer speakers, you can adjust the media player volume, and you may also need to adjust your system's master volume. The icons at the bottom of the webinar window include a resource list. Clicking that link will start the process to download copies of the slides to be presented today. This week, we have a slightly different format, and we will be using a pre-recorded video for the presentation. Hopefully, everyone's networks will cooperate, but if not, don't forget that there will be an archived version that can be accessed later. The video that will be played will play in the media player, and you may need to adjust the format of that, the size and the audio associated with that. Also, we'll still be taking questions and answering them in our standard live format with the presenter at the end of the presentation, so please don't forget to submit your questions. Now let's introduce our speaker. Dr. Steve C. Cripps obtained his master's and PhD degrees from Cambridge University in the 1970s. After working for several years with the pioneering gallium arsenide group at Plessey Research, he immigrated to the United States, where he worked for 15 years in various engineering and management positions at Watkins Johnson, L'Oreal, and Solaritech. In 1996, Dr. Cripps returned to the UK, working as an independent consultant before taking on an academic post at Cardiff University, where he is currently a distinguished research professor. Dr. Cripps has authored several best-selling books on RFPA design and is a regular contributor to the IEEE Microwave magazine with his popular Microwave Bites column. Dr. Cripps is an IEEE Fellow and was the 2008 recipient of the IEEE Microwave Application Award. So now it's my pleasure to provide this previously recorded presentation by Dr. Steve Cripps on the Load-Modulated Balanced Amplifier.
Good morning, everybody. I'm glad you have managed to find this area, what does he call it, studio, at such an early stage of the proceedings. So well done on that. And I imagine there'll be one or two people wandering in during the course of my talk. So I think we probably should, however, make a start. So I'll explain myself a little bit as far as the title is concerned. What I'm actually going to talk you to is actually a moderately serious subject, actually, which is something we're working on at Cardiff University. That's now primarily where I spend my time, at least time that I get paid. I call it Load-Modulated Balanced Amplifier, the LMBA. It's been quite a big focus for research in my area at Cardiff. And I've sort of come up with this thing about the old dog has a new trick. Now, you know, I know some of you may be not quite so familiar with English expressions, but in actual fact, the English expression involved here is that you cannot teach an old dog a new trick, you see. That is actually what the expression says. So the idea here is, you see, I'm the old dog, and in actual fact, I have got this new trick. But because you can't teach an old dog a new trick, I still sort of wake up in the middle of the night wondering whether it's all wrong, which in actual fact is what one or two people have already said about our paper that we published 2 years ago on the subject. They keep writing in saying we've made mistakes in the maths, which we didn't. And I am indeed, have been in the microwave business long enough. You go way back to the 1980s and the 1990s, And I'm going to just jump ahead a little bit here to my second slide. This is what we were all doing in the microwave business. This whole conference, really, which of course was much smaller in those days, was all about designing circuits like this. This is hybrid circuit technology. This was before microwave integrated circuits were really, well, they were probably being thought of, but that was about all. They certainly weren't very practical. This is a hybrid microwave circuit. You have some, I don't know, have we got a pointer? Do we have a pointer now? That takes me away from the microphone. We don't really have to dwell on this, but this is the kind of circuits that we were developing. It's thin film technology, alumina substrates. Quite small, you see, that whole sort of module there, that's basically about 6 millimeters. You know, it's quite small, really. You know, I mean, you think yesterday I was seeing some 5 millimeter balanced amplifiers on a GAN chip. You know, I mean, it's not so much. We're not talking in any way an order of magnitude scale here. Perhaps discrete transistors, I won't bother pointing to them. And the key thing is you have these input and output. These are interdigital couplers. And this is the quadrature balanced amplifier, which I say as my second bullet here. This used to be the default approach, really, to designing broadband amplifiers in the pre-MMIC era. More schematically, what you have here are 3 dB couplers. So it's a very, very good old concept. And in some respects, I still think we should see more of it today, because the whole point about this is that the couplers make the whole thing cascadable. If you're designing over a broad bandwidth and you want to get flat gain, you are, to some extent, going to have to mismatch at the low end of the band, you know, in order to equalize. Now, you can get clever and do resistive matching and so on, but I mean, you are still going to be reflecting power from if you just do a single-ended design, which means when you start cascading them together, you run into all sorts of problems. I still see it, actually. I still see that happening, particularly with MMIC designers. You know, once you start designing multi-stage amplifiers that are single-ended and reflect to each other, you can get into a lot of trouble quite quickly. And this was, I say, a grand old concept, that the reflections from the two identical parallel stages are actually phase cancel. They go through this 90-degree coupler twice, so that where your input is, the two reflections cancel out, the 180 degrees out of phase, and in fact the reflected power really gets dumped in the port, in the termination there. So basically, you can maintain a good match over very wide bandwidth, regardless of the fact that whatever you're doing in between the couplers, that's almost invisible. You know, you don't see what dirty work is going on between the couplers. And by the way, if we're talking more power amplifiers, this was used in low power as well, in gain stages. These are very, very good power combiners as well. They work very well as power combiners. So that's basically what a balanced amplifier was. It's sort of under the general heading. I could probably talk about this for the next hour, actually. This is a bit of a part of my past, quite a whenever I put this slide up, I almost want to talk more about it. I spent a significant part of my life designing these kinds of circuits, and you can see one of the things that I can never I never resist the opportunity is what we call the chicken pads, you know, the little pads there with bond wires. So I used to sit there all day pulling these bond wires and putting them back on again to flatten the gain, you know, over the band. And of course they all tell me, oh, you know, you shouldn't have to do that if you have proper models. It's got nothing to do with models at all. It is just simply manufacturing tolerances. You know, if you're cascading these things together to make a 30 or 40 dB amplifier, you know, you're just up against manufacturing tolerances. It's got nothing to do with how well the circuit was simulated in the first place. So what is the LMBA? It is an interesting extension to the concept, and I wished I'd thought about it back in that era. There's really no reason that we could not have done this back in that era, the grand era of the balanced amplifier. We could have done this, but nobody ever thought of it. Basically, the key concept is to inject a control signal at the output coupler rather than terminating the output port. Normally, you see, you go in at the top left and you come out at the bottom right, and the other two ports are terminated. If we actually push a signal back in at the output there, now, of course, and I have to be careful about this or clear about this, when I say a signal, it's not any signal, it's the same signal, you know. I mean, this is a signal that is frequency and phase coherent with the actual signal that you're trying to amplify. In fact, it probably will be derived some way or other from the input signal itself, possibly with a buffer amplifier, as I'm showing there. So what this does, surprisingly, and it is still, it would seem somewhat counterintuitive to many people. So we're injecting signal. Basically what this does is it modifies the impedance which is being presented to these two transistors. As I'm showing it here, you see, there's no actual passive matching. There normally would be some passive matching from here to match the output impedance, do the power match or whatever it is, to the 50 ohm. Obviously the couplers here are presenting 50 ohms. But if you start turning up this signal, injecting into this port here, then you will modify that impedance. So as I'm showing here, this is shown to be a very effective and very efficacious. That's a bit of a fancy English word. What I really mean by that is it's actually, you get a lot for your money. In other words, it is one of the surprising things that comes out of this analysis of this configuration is that you get a large amount of action. You can pull this load around a large amount with a surprisingly small amount of power. So that's all in the maths. And so let's just quickly summarize the maths. We do have publications out which go into this in somewhat more detail. What I'm doing here is I'm taking the 4-port matrix of a coupler, and there are two transistors. We've basically got 3 current sources here, except there's 2 of them shown as current sinks. So the 2 balanced stages, you've got I-bal there, you've got a minus J I-bal there, and so that means that in normal balanced operation, the power from those 2 current sources would come out in the termination here. But now we're putting a 3rd current sink, as I'm showing it here. That's the control. I call that's the modulating. This is the control signal. We vary the amplitude and the phase of I mod, and that causes the impedance, which is seen by these 2 transistors here, to change. So there's quite a lot of exclamation marks around here, because in fact, although our original paper on this appeared in the Microwave Components Letters now just about 2 years ago, there has since then been a considerable amount of question as to whether it was all correct. And of course the problem is you do have to be very, very careful to get the signage correct on these various currents, and that's caused a certain amount of confusion. But anyway, without getting the maths too much, once you've established the direction of your currents, you can calculate you get 4 equations which calculate the voltages at the 4 ports. From that, so this is an ideal 3 dB coupler matrix in actual fact. From that, you can determine what those impedances are. So I'm giving a little bit of details of the maths here which you need to go into. So Z2 and Z4, those are the 2, what I call the 2 balanced ports, the 2 transistors. So I mod is the modulating or control current. So obviously in these 2 expressions, if I mod is 0, then obviously each transistor sees Z0. That's the home impedance, as we call it, of the coupler, usually 50 ohms. But then this subtractive term here has the form of this is the ratio of the modulating current, as we call it, to the actual main current in each balanced transistor. So obviously, if, for example, that approaches unity, that ratio, we're achieving quite a substantial load modulation. I'll show you the inevitable Smith charts in a minute, but again, a whole load of exclamation marks and question marks. This is really a little bit of a private joke amongst me and my colleagues at Cardiff, because there has been so much correspondence about these equations, in particular as to whether this should be a plus or a minus sign, which is entirely dependent on the way you specify it, the way you set the thing up in the first place. The point being, of course, phase comes into this. I mod is a complex number. It's not. We are not just simply modulating it resistively. Admittedly, okay, if I mod and I-bal happen to be the same phase, literally the same phase, you would be modulating the load up and down the real axis, which is indeed, of course, in terms of power back off, this is a Doherty-like performance. The point about the LMBA is it can do a great deal more than that. In a sense, the Doherty load modulation is up and down the real axis. Well, yeah, we can do that if I mod and I bal are in phase with each other. But in the LMBA, I mod is going to go all the way around a full, 360-degree phase. So in that sense, the sign of that term is really redundant, because it's really all just dependent on the relative phasing of those two terms. So this is actually just showing a simulation. Again, this is one of these things you come up with these results. I certainly found it somewhat counterintuitive, I have to be honest. I mean, it's something that I've come up over the years. I have thought a bit about this. What happens if you put in power at that port? I had always myself intuitively felt that the impedance would not be the same. Because of the 90 degrees, I almost felt, one would go this way, another would go this way, and it wasn't going to work. The equations said, hey, look, it does work. And so one of the things I often do, I always like to say, I'm not really these days being an academic. I don't really design products, for production sort of thing anymore. What I actually frequently use the simulator for is to check my maths, The simulator doesn't get things wrong, whereas I do get things wrong when I mess around with, J's and minus J's and all the rest of it. So although I'm not going to run this live this morning, in fact, you can see that this is a direct microwave office simulation of the precise circuit that I was just showing you the mathematical analysis for. So there's two current sources here in 90 degrees out of phase. You can see 90 there. And what we're doing essentially is to vary the magnitude and the phase of this injected signal here. So using what I still regard, don't worry, they don't pay me to make plugs, believe it or not. They don't actually pay me to make plugs about microwave office. In fact, actually, they almost tell me, Steve, back off a bit, don't make it too obvious. So I think I'm not very good at doing subtle plugs. My plugs are really, kind of pretty big kind of plugs. The parameter sweep is a very, very nice feature on microwave office. I find it very easy to use. I mean, here we've got this thing. I mean, obviously what I want to do is to say, well, what happens if I sweep the phase of that through, 360 degrees, right? No messing about. You can just simply right-click on the angle there, and you can set up a sweep, which you can see is minus 180 to 180. So that's sweeping the actual phase of the CSP. This term CSP, we originally started saying, we call it the control signal power. We didn't want to call it an auxiliary input because we felt that people would confuse us with a Doherty PA, which you often call the load modulating element is called the auxiliary often. So I didn't want people to sort of start thinking that what we've got here is some kind of a Doherty PA variation, as it's not. And that's really the main point I'm trying to make here. And perhaps that becomes clearer if I actually show you that, because I'm not going to show you that live. But here is what happens if you can see I've set 3 levels of CSP there. So you can see we're sort of starting off. Obviously, if the CSP is 0, if we turn that off, we're at the 50 ohm point. We've got a single point in the middle of the Smith chart. As we go to, I've got 3 different ratios there of current. So it's 0.2, 0.4, and 0.6. Bear in mind they are current ratios. So, of course, the power ratios are quite a lot smaller than that. And you can see how we can literally sort of, cover quite a significant area of the Smith chart. The big circle there, and by the way, it is possible to join those points up. I, of course, didn't do that in order to make it clear. Sorry, this is a bit of a private joke, actually. I couldn't get the points to join up when I did this, but obviously you can do that. So that big circle there, you see, that is in fact round about half of the current. So, we're still some considerably way down. Most of the time when we do this, we find we can get a very, very useful range of impedance modulation for power levels, the CSP power levels, round about 10 dBs down from the actual main power coming out of the amplifier. Which brings me to the next, in actual fact, that's slightly clearer on this slide. On this slide, where you can't just simply square the current because, of course, the impedance is varying as well. So to figure out what is the actual power ratio between what the amplifier itself is generating and what you're having to stick into that port, the ratio of that power is obviously an important parameter. Excuse me. You have to take account of the modulated impedance. Obviously, you're changing the impedance, so you have to take account of that as well. If you do that, interestingly enough, you do actually get concentric circles on the Smith chart, which now gives you a slightly clearer picture. I've actually labeled in dBs there, you know, the power level that you need to inject in order to get that particular circle. And bear in mind, of course, you know, obviously these are filled-in circles. You know, I mean, basically by setting a particular amplitude and a particular phase, you can find any point in the middle of anywhere inside one of those circles. And so that's just a slightly more refined way of looking at it. But this brings me now to what has been probably the most, to me, not remarkable, because I think it's just something rather fundamental, but what in general has been the most controversial aspect of all of this in the last couple of years. Only yesterday, somebody comes up to me and says, oh, this business about your LMBA can't possibly be right. Whatever power you stick into that port comes out again. You don't lose it. I was never very good at chemistry at school, but I always remember catalysts. It's a bit like that. You know, you stick this power in and it does some useful things. It modulates the impedance, it improves your efficiency, but you don't lose it. You get it back again. And the reason for that is you don't really have to do, our reviewers, when we did our original paper on this, were total disbelief about this. They said, that's got to be wrong, can't possibly. All we're saying is, if you've got a completely passive structure, right? I mean, a 4-port coupler is a completely passive structure. If you measure the power at 3 of the ports, the sum of those has to be what appears at the 4th port, because otherwise you would be absorbing or reflecting power. I mean, okay, there's a bit of loss, all right, you know, but these structures in general are very low loss in actual fact. And it is, as I say, a simple consequence of the properties of a passive network that this in fact happens. But time and again, people sort of say, oh, well, yeah, but you're varying the phase. I mean, surely when you vary the phase, that that's going to change. But you see, but it doesn't. I mean, obviously things do change when you vary the phase. I mean, that's the whole point. I mean, you will see the output power change as you vary the phase because you're tuning the two devices. You know, as you subject your 2 balanced transistors to different tuning conditions, the power will change, the efficiency will change. That's the whole idea, really. That's the whole idea of it. So things change, but the actual, at any given point, at any particular power level and phase of the input of the control power, you will always regain that power. It will appear as part of your output, which is rather convenient. Just quickly going back to this plot here, just again readdressing this whole question of what's the difference between this and a Doherty PA, then it's important to notice really here that the impedance modulation is entirely two-dimensional. You know, we can go up, we can go down, we can go any way we want, and we will not consume any of our control power. You can't do that with a Doherty PA. You know, you can't do that. With a Doherty PA, you just simply have 2 current sources or 2 current sinks and a common load. That's okay so long as those 2 current sources are precisely in phase with each other and they see a resistive load, which then gets modulated. That's fine. But as soon as you start messing around with out-phasing or... Oh, did I say something? Out-phase... God, what? Wow, sorry. I didn't mean to mention the out-phasing word, but as soon as you start moving away from the in-phase condition, you will start consuming power, you know, and you will start losing power. That doesn't happen here. So that's the theory. I don't know how my time is going here. Oh, gosh, I've got lots of time, really. We have, of course, built a number of demonstrators of this technique. And this was the first one which we described in our June 2016 Microwave and Wireless Components letters. You can see that we're now using 2 drop-in, you know, commercial drop-in 3 dB hybrids. And being in the academic world, of course, guess what transistors we're using? You see, we're just as big offenders as everyone else, you know. I was saying to Ivan here, was it yesterday, you know, paper after paper after paper uses the Cree 10-watt transistor, you know, and it's sort of like, I think it's about time we had a workshop for papers that do not use the Cree 10-watt transistor, you know. It's sort of, you know, we like to think that we are doing something quite a bit novel here, you know, so, but these people who kind of do all this continuous inverted class F, G, K, W, you know, mode, and get 55% efficiency at their band edges. It's like you can get that if you just put this transistor in a 50 ohm. We did that actually. We took this transistor, we put it in a 50 ohm test fixture and measured it. Crank up the power. You get 55% if it worst. I think we got 65 at the best point. So it's a very, very friendly transistor, and I suppose I have a particular okay. Look, we're doing the same, but this is somewhat different. I like to think. I suppose having gone back to the time when I was trying to make a 10-watt amplifier using gallium arsenide off an 8-volt supply rail, that was a whole different. So I suppose I'm just a bit cynical about how easy things are today compared to the old days when you're matching down to 3 ohms or something like that with a 10-watt gas device, whereas here these devices are actually reasonably happy in a 50 ohm, which is what we've given them here. You see, let me just get my handy little pointer. Never done this before. Here you see on this particular test circuit, you can see that the output is pretty much going straight to the coupler port. There's a bit of bias. You've got to sneak in a bit of a bias choke there. But essentially it's a little bit of 50 ohm microstrip line and goes straight into the coupler on both sides. The input, we do have just a stub just to sort of flatten the gain. That just pull. That's horrible, that isn't the way it does that. That pull, I hate it when it does that. You pull up the gain at the high end, right? And so you get reasonably flat gain. So we really are here, in a sense, we are to some extent making life fairly easy for ourselves, in the sense that the transistor isn't too badly off with a 50 ohm load in the first place. However, this was just a demonstrator to see what we could do if we started putting in, various amounts. We threw this together. Dan Shepherd, who was my PhD student at the time, sort of threw this thing together in a couple of days, with parts that were more or less lying around, so that we were quite excited when we initially set this thing up and says, well, okay, wow, let's crank up the power and see what happens. And in fact, what happened was really very encouraging. These are basically, if you look at the black line first, the solid line first, that's what the amplifier does by itself. That's to say, if we just have a conventional, old-fashioned balanced amplifier with the output coupler terminated, just with a 50 ohm termination, excuse me, that's what you get. So, in other words, we were, getting just about the inevitable 10 watts. And obviously, that's what we get. There's obviously potentially should be a little bit more than 10 watts, really, the balanced amplifier. Having extolled the virtues of the quadrature coupler, obviously, this particular 50 ohm termination is not optimum. We are not actually getting, if it's optimally terminated, we should be getting more like 43 dBm, which we can indeed now get if we just look at this first loop here. What we're doing here is we are putting in a certain amount, not very much, of control power, somewhere around, in fact, I think he has got it marked down here, but basically about 10 dBs down, so we're getting 10 watts out, so we're putting about a 1 watt control signal, and we're varying its phase. Now, of course, this is being done with a second generator at this point. This is just a test bed, all right? So, we are indeed using a, 30,000 pound generator, which is locked to the main signal generator, phase locked, and we are just simply turning a knob. When I did the very first measure, I insisted, I waited for the student to go home because I wanted to be the first person to actually vary the phase, and of course, because I'm an old codger, I can't do it with software, because Dan came in the next day and, I was saying, oh, how's it going, Dan? Of course, he's sitting there writing software. This is the problem with students these days. You're all excited about getting some results. I thought, well, let's just turn it on and just kind of take a few points and just mess around with a couple of knobs and just get some, but oh, no. So you've got to go away and wait for a week while they write the software, the measurement, the test software. It can be really rather frustrating. So anyway, he went off and did that, and so I just got into the lab and started measuring some points myself, just by varying the phase, 10 degrees at a time. And I was, obviously quite pleased with what I saw. First of all, we were indeed able to tune the device. Now, to be fair, we could have done a better job with the initial design. I don't know well, I guess Tudor was in the session this morning where they were talking about Varactor tuning, and it's sort of like, well, yeah, I mean, it's all very well being able to retune a bad design. If you design something non-optimally, and then you go to all the trouble to have some kind of load modulation or Varactors or whatever it is in order to correct your bad design. I mean, that isn't really a terribly optimum way to proceed, really. But here, this is just a demonstrator. So we knew that this point here, for example, this device probably really wants to see more like, I think, 20, isn't it? 25 ohms, 30 ohms, I think, for this particular device. So, we're not getting our 43 dBm in the passive tune because there isn't any passive tuning. It's a lazy design. But as we started to retune the output, we could indeed get almost 43 dBm if we go to maximum power. See, this is one of the many applications that sort of starts to come to mind here. I mean, for example, we can use this ability to tune the device using external, electronic controls. We can tune it for optimum power or optimum efficiency. That is no longer a choice that we have to make with a particular design. We are able to actually hop between the maximum efficiency point there, which as you can see is quite high, that's in the mid-high 70% region, or to maximum power as you go around the loop. However, that said, of course, the real strength, or let's say the application that usually most people come to mind is back off, right? Obviously, being just a regular ordinary amplifier, as we back off, the efficiency plummets. This is regular, standard, It's probably the reason most of us are here this week and have been coming here for the last 10 or 20 years, right? I mean, that is the problem. As you may do a reasonable job, maybe you could do a slightly better job, you see. I think if we actually did, this came up, this was one of the reasonable questions that came amongst many unreasonable questions when we had our paper reviewed. Somebody made the point. It says, well, yeah, but you could just do a better job with your passive matching and hit one of these points on this loop. Not quite true, it turns out. I mean, a reasonable question. We could have done a somewhat better job. But bear in mind, we are recovering this 1 watt of CSP as well, so that we actually get a little bit of a power bonus as well when we do it this way. If we did it with passive matching, yes, we would probably be able to get a bit better efficiency and or a bit better power. We would not actually hit these points on this loop for that reason, that we are not, we are feeding more power in and we get it back. But of course, as we back off, you can see, for example, here, we go down, this is like maybe 8 dBs to the 32 dBm point. I mean, the amplifier itself is down at 20%, or mid-20s, whereas we can, in fact, retune it all the way up into the mid-50s. We are not able to retune it up into the 70s for the simple reason that when you back off a Class AB amplifier, of course, the current waveform is changing as well. As you back off a Class AB waveform, the current waveform becomes more and more like a sine wave again, so that you can't ever expect, even with merely using output load modulation by itself, you will never be able to reach the dizzy heights that you can at full drive. So this was quite a pleasing little sort of demonstrator. We got quite a lot out of it. I know when I was many years ago actually working in America, we always used to have this, the first grubby little kind of, demonstrator, the first sort of little test circuit that we ever made always worked best. You sort of, it always seems like, you're sort of, we used to call it the law of the initial maximum. Particularly this used to apply to, things like the circuit I showed you, which is a design actually. That's a 6 to 12 gain stage, which we did some way back in the mid-80s at Celerite. The one that you yourself sort of tuned up and spent a couple of days tuning up, you sort of release it to production, and it's like the performance goes down at about 1 dB per 3 months, I used to find. It was about that, You start off, I think that thing had about, this was old, this is 1 micron gas FET days. I mean, 6 to 12, you didn't even get 10 dBs a gain. It's probably more like 8 dBs a gain. But it was sort of like, you know, you go into the production area and talk to the lead there, and he's saying, oh, this 6 to 12 circuit, oh, you know, we're getting 5 dBs against you. What? So there is a bit of that in our subsequent. It's still a fine concept. However, our sponsor for this work is not in telecoms. They were in the ECM business. They are in the ECM business. And I should say, by the way, sorry, I'm jumping ahead of myself a little bit here. I'm sort of ad-libbing here because I realized I got through that material a little bit faster than I thought. I should have shown you this slide. The other dimension we've got here, you see, is frequency tuning. This is the whole point, that although people think Doherty, PA, you know, back-off efficiency, fine. That's if you're in the telecom sector. That's very important. And you're maybe not dealing with such broad bandwidths. But, of course, in the military, in the ECM sort of applications, you're dealing with broadband. And that's where, particularly as you go to higher power levels, you know, you do run into problem with passive matching. You know, you run into, you know, I'm not even going to mention Fano, you know, because I've never even understood Fano's theorem properly. But anyway, you know, you run into some fairly fundamental problems in terms of trying to match, you know, larger, higher amounts of power over broader bandwidth. So that the LMBA has this additional dimension, if you like, in terms of its application, that you can actually retune your matching over a broad band, you know. And that's what we're showing here, although this isn't actually an ECM, obviously, application. We're still down in the 2 gigahertz range. But what we're showing here is you see that really the only, these results can be replicated at any frequency that's within the coupler bandwidth. You know, the only bandwidth limitation here is the actual bandwidth of the coupler. As this is showing you here, we're getting fairly similar. I know there's a lot of lines there, but you can read the paper. It spells it all out a bit more. I know you've got small print. You probably can't read there. But essentially, we're able to replicate that performance that I showed on the previous slide at a wide range of frequencies that are within the coupler bandwidth. And that's a very important additional sort of property that we are, in fact, utilizing that property rather more at the moment. In fact, that's to say optimizing particularly efficiency over a broad band, say like a 6 to 18 gigahertz type band, rather than being quite so worried about power back-off, but it certainly does perform, obviously, in power back-off mode. This is one of our first attempts to move this whole concept up into X-band, and again, I always just don't like to throw too many results at you. This is actually a 6 to 12 design, and this is done on this is actually liquid crystal polymer type circuits. So these couplers are these are not your standard Lang couplers. These are actually broadside coupled. So this was our first venture, and indeed this is also published in the fairly recently in June 2018, if you want to actually see the performance on this. But rather than showing you those set of graphs, what actually I'm doing is that the next step on is the more recent result. This is an actual MMIC. This, I believe, is a 3mm chip, in fact. And this has got integrated, the CSP driver stage is integrated. So you can see that's a much smaller transistor. In fact, it's about the same size as the driver transistor over here. And then these are the 2 main transistors. So this is a more recent result which integrates some of the functions. We still need to do the phasing of the CSP input. Now, in our application, which is I'm not allowed to say what the application is, am I? Gosh, no. But it's a military system application where it is actually okay to ask for a signal at a particular phase. You know, it's something within the system. They're generating, you know, this signal at lots of different phases. So it's not actually a big ask, if you like, in the particular application we're doing. So that's the reason we don't actually we don't bring this all back. All of our LMBAs are double inputs, you know, because the system that these things are aimed at is able to handle that. You know, we are able to say, hey, look, we want this signal at this power level, at this phase, you know, at any given time. Whereas in more of the telecom band, people want a single input amplifier. And in fact, this is where there's been some very good work done on LMBAs by my good friends at Boulder, Zoya. Don't think is here. She said she was going to come. Not Zoya and Taylor. Both have done some very good work there, where they actually do rather than having the CSP as a separate input, they actually they couple their CSP signal from the input signal, so it's all a single. And then they have this rather clever filter thing, which actually manipulates the phase over a whole octave band, in actual fact. They've published quite a bit on this. So this thing, again, there's an awful lot of lines here. One of the reasons there's so many lines is that this particular application, we are changing the supply voltage as well. So this, again, gives you yet another example of how you can use the load modulation properties of the LMBA. If you are actually varying the supply voltage to control the power, then you can actually, retune, if you like, the device to get optimum performance at different voltages. A lot of people think that, envelope tracking automatically gives you maximum efficiency at all times, and of course it doesn't. And so, roughly speaking, what we're really saying here is that over this band, which is sort of low part of X band, we are able to get efficiency above 40%, which is a bit of a sort of that's very much a line in the sand, it seems, on these applications. I think if you go into the literature, tour around some of the booths out there, I think you'll find people have got X-band, KU-band mimics, but their efficiencies are more down in like the 20% region. That's pretty much more the path of the course. Our goal is really to achieve more like 45% efficiency and over considerably wider bandwidth. That work is ongoing. I'd like to show you some of it, but at this point, I'm afraid it is under wraps. So, yeah, the LMBA, so just to summarize, appears to be a long-sought solution to broadband PA efficiency. That's the key, is the broadband. Broadband PA efficiency enhancement for modulated signals, if that's your application area. But it can also be used for fine-tuning, or even maybe in some cases not so fine-tuning, of a medium power amplifier, even to the extent, for example, of replacing hands-on tweaking, all those little chicken pads. You could replace those chicken pads with really a very small amount of injected signal, varying the phase, would have very similar and possibly rather more well-controlled effect. In terms of conclusions, I think that active load modulation is still a developing area in the microwave design community. I think it took us a decade or two to get our heads around the dirty PA and what on earth was going on there. The idea of using a second generator, a second device, a second active device, to modify the impedance that the first device sees is still quite a difficult concept, I think, for an RF designer. We're brought up to think that matching and changing impedance is all Smith charts. You've got to sort of get your Smith chart out and its transmission lines and inductors and all this kind of stuff. Whereas, in fact, there is another way to do it. The dirty PA obviously is widely recognized as a demonstration of these benefits, but in fact really does use them in a very restricted manner. I have, as I say, I almost dared not mention the Schreck's out phasing circuit. That is another demonstration of load modulation and is certainly a bit more of a wild beast, in my opinion, but there we go. So the LMBA, I think, is going to emerge as an important new player in RFPAs, taking the application space beyond power management into more general reconfigurable applications. So that is essentially all I have as far as the slides are concerned.
Okay. Thank you, Steve. That was really an excellent and informative presentation. So I'd like to welcome Steve onto the audio now. Are you there, Steve?
Yes, I'm there, and there have been some very good and very perceptive questions, so I will try to answer them as best I can, even if I can't completely answer them to the full satisfaction of the questioner.
Okay, sure. Yeah. So you're right. It is time for our question and answer session. And before we start that, just remember too that questions can still be submitted through that Q&A panel. So let's just go ahead and jump right in, see if we can get some of these questions answered. Let's see. I'll just pick one of these randomly here that we've marked. Does the injected amplifier need to have 50 ohm output impedance, or can we modify the coupler to deal with some other impedances?
Okay, I think that's a more straightforward, a perfectly reasonable question. The CSI port, the port where we inject the power, is fundamentally 50 ohms. That is because you've got a balanced amplifier. So long as everything's balanced, so long as the coupler is a reasonably balanced 3 dB hybrid, that will always present a 50 ohm load to the whatever presumably amplifier you're going to use to generate the CSP. So yes, obviously it would certainly help if that amplifier is designed to work into 50 ohms, because that's what it will be working into, and as with just about any other amplifier, so that is absolutely correct. I mean, if it's designed to operate into some different load, then you will get some mismatch there and you will lose some power. But yes, the CSP port presents a good, solid broadband 50 ohm load.
Okay. How sensitive is modulation power recovery to hot S22 of the core PAs?
That, I think, is the question that I commend the questioner. It's still something that bothers us a little bit, in the sense that there is, I don't want in any way, after all of what I've said about a 4-port passive device. I mean, fundamentally, those powers will still add up, but there is this question about, in particular, when a device drops into its knee region, is it possible that the device itself can start stealing some power? We've not seen it, actually. All of the demonstrations that we've done, we do seem to manage to recover the CSP. Obviously, there are losses. You do have to take account of the coupler losses and so on. But so far, we've not seen it. My experience in all of this, and people talk hot S22, all of the years I've worked on PAs, I always feel that the current source model is pretty robust in actual fact. Whatever you may think about the slope on the IVs and the knee factor and all the rest of it. So it's a good question. It is actually something that we are taking a closer look at, in particular with regard to whether this interaction may be better or worse with different kinds of device. The GAN device does have a soft knee, and it is still something of a concern, but it's certainly not something that we have been particularly troubled by in terms of the numbers that we're seeing. That's about the best I can say. We better move on, I guess.
Okay, yeah, no, sure, that's great. There's several questions here about harmonics.
Yes.
This one in particular, can you comment on the role of harmonics and waveform engineering on the performance of LMBAs, and then also from the perspective of injecting that as the control center, or the control signal?
Yeah, there is a fundamental problem injecting harmonic, and you will no longer, unlike with the fundamental, where the impedances modulate together in sync. That will not happen with the, if you go to a second harmonic. Unfortunately, in that case, you will be, the phase of the second harmonic that will appear is basically 180 degrees rather than 90 degrees. If you think about it, that's the coupler will still do a 90-degree split. So you inject your, say, second harmonic, you'll get a 90-degree split between the two devices. Whereas in fact, what you want is 180. If you do your sort of cos omega t plus pi by 2, the second harmonic of that is cos 2 omega t plus pi. That's what you want, and the coupler doesn't give you that. So it's not as straightforward as simply injecting a harmonic. And that's, I guess, one reason that we have not seriously investigated that. But there are probably ways around it. It has not escaped our attention that there are ways around that problem.
Okay, great. So possible area of future work there. Okay, can you please comment on the linearity of the LMBA with respect to Doherty PA or just in general?
Fundamentally, the LMBA does not have the sort of the linearity of the DOTPA. The DOTPA, it's a sort of a funny sort of good news and bad news and good news in a way. The DOTPA, to achieve the 2-to-1 impedance modulation, you need the same amount of power from the CSP, if you like, or from the auxiliary, as compared to the main device. So that's the bad news, if you like. It's sort of like getting that 2-to-1 impedance transformation takes a lot more power. You know, we can do that with about 10 dBs down, 10 dBs less power. We can get that same 2-to-1. But the problem then is that when we recover the power, it is only really a small add-on to the main power. So that the end result is that you end up with a device that's maintaining constant voltage, constant high efficiency, but in fact the relationship of the output to the input fundamentally will have a sort of square root characteristic. Now, these days, that isn't such a big problem because you can handle that with the digital pre-distortion. And in any case, what you can do is also play some other tricks. In particular, if you can, with the load modulation, you can push the device into its clipping region, and you can, in fact, reduce that effect to a considerable extent. There have been several publications in the literature showing an LMBA giving excellent linearity, with an LTE, fully formatted telecom signal. So it can be done, but I would certainly say that fundamentally that there is a difference there.
Okay, let's see. On slide 14 is the efficiency, the drain efficiency.
Yes. This has turned out to be, again, one of the most, particularly when dealing with reviewers, has been a very difficult topic. I mean, to answer the question, yes, it is drain efficiency of the main amplifier. So in other words, we are not considering the efficiency of the CSP. I mean, the point about power added efficiency is that, in a sense, you put your drive signal in. I mean, you do actually lose that. You've got an amplifier. It's got 10 dBs of gain. You put 1 watt in, you get 10 watts out. You don't get 11 watts out. There's a difference here that in the case of the CSP, if you've got a 10 watt amplifier and you're sticking a watt in to modulate the impedance, you do actually get 11 watts out. So it is a bit different. And so really in our early work, we did report, and I think we made it very clear that we were doing this. We did report the drain efficiency. That's to say we were not taking account of the drive power, and we were not taking account of the CSP either, simply by way of illustrating the fact that we were able to tune the device to its optimum performance. In actual fact, at the end of the day, obviously, you do have to take account of all of these different powers. I still have a little bit of an issue on this in the sense that, for example, you go back to power added efficiency, which is what systems people always like you to quote. I mean, yes, you take account of the drive power, but you are normally not required to take account of the efficiency at which that drive power is generated. And that's where I sort of draw the line as well. I say, look, that's a bit unfair. But certainly when we quote those results on the MIMIC, I mean, there is no doubt about it. You have to obviously, you just simply have to quote total RF output versus total DC input. I mean, but that's moving into the system regime. When we're demonstrating a single stage amplifier, I think it is entirely appropriate to quote drain efficiency whilst recognizing the fact that we are feeding in a certain amount of CSP, but we are recovering that at the output. It's a more complicated issue than you may at first appear. But to answer the question, that initial result, we are quoting drain efficiency by way of illustrating the fact that we are able to tune it.
Okay. Okay, I think we've got time here for another couple of questions, and please also just continue to submit your questions, and we'll try to either get those answered online or offline.
Yeah.
So there's one here on the reflected power from the load will dump into the CSP port. So does it mean the CSP source impedance needs to be close to 50 ohms?
Yeah, I'm just trying to read this again.
Okay.
In the analysis, you know, I mean, with the CSP is simply a current source. So, I mean, it is not 50 ohms. In fact, no, that is not a problem.
Okay.
We've got to move on a bit. I realize that one could get into a discussion on that, but that would be my quick answer.
Okay, all right. Well, maybe here we'll just, there's several questions here about bandwidth. How much additional bandwidth, needing to tune the different transistors differently. Could you make some more comments about the bandwidth? Yes,
I mean, the bandwidth of an LMBA is almost entirely determined by the bandwidth of the coupler. In fact, even there, it turns out that it is sort of remarkably tolerant of even the sort of, you know, if it's a single section coupler, it is actually quite tolerant of even the small deviations from 3 dB at the band edges. So that is essentially the band limitation. There is really no other, and it is one of the you know, important properties of the LMBA is that you know, the bandwidth is not you know, there is no fundamental. We don't have, for example, an impedance inverter which is band limiting. We don't need that, and the bandwidth is essentially determined by the bandwidth of the coupler, which of course does mean, you know, that you are, if you're trying to design something, you know, 10 megs to 10 gigahertz, you know, that does raise a problem as to how do you implement the 90-degree hybrid. So there are some limits on bandwidth.
Okay.
Multi-octave.
All right.
Yeah.
Go ahead.
Yeah, multi-octave would be problematic. Yes.
Okay. Okay. Do you see any of these other questions here that stick out?
I think you're saying, well, I think there's another one about bandwidth, how much additional bandwidth extension. So I think we've answered that one.
Answered that one, yeah. There's one about applications at higher frequencies. Any comments or questions there?
We've been essentially working up to 20 gigahertz, but we're not able to, we have, to date, we've not actually been able to publish those results, but we are hoping. There's some patent disclosures gone in, and so we hope that we will be able to publish some of those results. But certainly, yes, we don't see any bandwidth limitations. If you can make a coupler, you can make an LMBA.
The math still works at those frequencies.
Yeah.
Well, that's great. Okay, well, I think that's a great set of questions and answers. Thank everybody for submitting those. And we are essentially out of time here. There are still a few questions in the queue, and we'll ask the presenter to follow up with those offline. Also, as we said earlier, this session will be archived on the Society website at mtt.org. All registrants will get an email reminder with a website address when that's available. For attendees who would like to receive PDH credits, please follow the link in the webcast view and use the code that's provided on the last slide here that's being shown right now. Once again, I'd like to thank Dr. Cripps for this excellent and informative presentation and for the new format today. That was great. And special thanks also to our audience for joining us today. We hope you found today's event valuable and that you'll return for future IEEE Microwave Theory and Techniques Society webcasts. Thank you and have a great day.